Alright people, welcome back to the next lesson. And the next lesson is simply supported beams. Now if you think back to the first time we spoke, I spoke about the three topics that we're going to continue in theory of structures. Well, this is the next one. Remember we did beam reactions? Well, here we go. There's the first question there. I'm going to work through an example and explain bits as I go along as I do the example. This is referred to the simply supported beam shown below. Well, that should actually be next door. Not below, should be next door there. And answer the following questions. Number 8, calculate the support reactions. You know all about that because you did millions of them in the prime mechanics. Right, the people there we have a pin joint, there we have a roller joint. And I'm going to draw in where the reaction should be. So let me do this quickly. So that's a pin joint. And because there are loads acting downwards, I'm thinking there should be loads acting upwards. Oh man. And there should be a load reaction acting upward like so. Are there any horizontal forces acting? Are there any horizontal forces acting? No, there are no horizontal forces acting, so this HA is going to be equal to 0. There we go. Okay, so we want to determine VA and we want to determine VB. Okay, right, so people now, yeah, so I'm going to take moments about the pin joint to find VB and take moments about B to find VA, or another way. Right, so I'm going to say number A. Go here, A. Right, sum of moments about A is equal to 0. We know why that's the case, because the whole system is in equilibrium. Right, so that's going to be minus VB. Why is it minus VB? Because VB is anti-clockwise with respect to A. And what's the lever arm for BB? It is 8 meters plus. Right, can you see there that all the loads on the beam are going to be clockwise with respect to A? Now this here, we call this a point load. That's a point load. We call this a point load. Point load. Maybe I should write it there, point load. Point or concentrated load. Concentrated load. Okay, I'm going to mess on here a bit. Okay, for example, in a structure, a column is a point load or concentrated load. That's an example of a point load or concentrated load. Okay, and this here, this 15 kilonewtons per meter, notice there's arrow showing down, that is how we show it. Or from the second example onwards, I'll show it as a squiggly line like so. Okay, and that we call a uniformly, a long word, uniformly distributed load. And because we're all lazy human beings, and I don't know, we seem to love acronyms, call it a UDL for short. Okay, so that there is a UDL. Okay, and an example of a wall, you know, a wall, that's a UDL. Okay, means if I take up a meter of this and I put it on a scale, it will weigh 15 kilonewtons. Okay, so every meter, this thing is 50 kilonewton meters long. Okay, wonder if I can clear this. Oh, good, I can clear it, lovely. Right. Right, I'm taking my point load. So, I'm taking moments of it A, so this will be plus 100 times 2. Why is it times 2? Because the definition of a moment is a force times the perpendicular distance, and all of these forces here are acting at right angles through the point of rotation. 100 times 2 plus, changes to blue. Right, UDL, are you tuning in? This is a force, so many kilonewtons. This is a force per meter. And a moment is a force multiplied by a distance. Okay, so we need to first work at the total load due to the UDL, and it weighs 15 kilonewtons per meter, and it is 8 meters long. Okay, so what's the total load due to the UDL? It is the value of it multiplied by the distance, so it's 15 times 8, so it's 15 times 8. But that there is only the force, and we are taking moments, so it's times the distance. What is the distance? Right, are you tuning in? The distance always acts through the center of the length of the load. The lever arm for UDL always acts through the center of the length of the load. How long is the load? About point A? It is 8 meters, so it is times 8 divided by 2. Okay, so that means if I drew an arrow with centroid where it's acting through, from there to there is 4 meters. Okay, are there any more? So now it's equal to 0. Okay, so now we can make VB the subject of the formula. Okay, and if we do the calculation there, I get VB. Okay, don't just take my answer as correct. Check the answer, stop the video, check the answer, and see if we get the same. I get exactly 85 kilonewtons. And because it's positive, it means that my assumption that it's going up is in fact correct. Okay, so VB is 85 kilonewtons. And that was a walk in the park, isn't it? Easy, easy. Right. VA. How do we find VA? We can either take moments about B to find find VA, but at this point we're getting a lot smarter. We are going to sum vertical forces to find VA. Okay. And of course that must be correct to do so. If that's wrong, and if you sum vertical forces, VA is going to be wrong too. Okay. So let me just clean the board quickly, and then we sum vertical forces to find VA. Right, I'm now going to sum, and I'm going to say the sum sum of the vertical forces is equal to 0. So it's VB, which is plus 85, minus 100, minus 15 times, remember, that's a UDL. And the total load due to the UDL is 15 multiplied by the total length times 8 is equal to 0. Okay, right, so do the calculation, oh, man, and check mine and see that you get the same as mine. And I got VA, right, let's see, therefore VA is equal to 135 kilonewtons exactly. Okay, there we go, it's equal to 135 kilonewtons. Okay people, so that's part A done. We calculate support reactions, and because there's no horizontal forces acting, HA is equal to 0. Okay, right, so let's go on to part B of the question. Right people, I want to continue. I'll clean up the board a bit, and I'll just move things around a bit. Sorry I have to make this a bit smaller. I'm trying to make it smaller, but as big as possible for you to see it. Okay, and the reason why I'm doing this is because whenever you do this, are you listening to me? Whenever you draw the next part of the question there, says draw the shear force diagram, draw the bending moment diagram. Okay, so whenever you do a question like this, you always start the question at the top of a new page. Did you get that? You always start the question at the top of a new page. This here is the load diagram, and below this we draw the shear force diagram, and below that we draw the bending moment diagram. Okay, so you're going to have 3 diagrams on one page. Okay, and the 3 relate to each other, which I'm going to explain. So you start this load diagram at the top of a new page, you draw the shear force diagram below that, and then you draw the bending moment diagram below the shear force diagram. Okay, right, we're busy with part B, draw the shear force diagram. Right, so here we go. Now people, now whenever you draw this diagram, draw to a good scale. Now when I say a good scale, doesn't mean you must take a rule and work it out like you do in engineering drawing. That's 2 meters, that's 6 meters. Okay, that means this length here is about 3 times longer than that. So if, okay, so you can see that this distance here is shorter than that. It's about 1/3 of that. So draw to a reasonable scale, because the shear force and bending moment diagrams are actually it's actually scale drawings, but to a reasonably good scale. Right. So the next thing I'm going to do is I am going to project. Okay, I'm going to project this down like so. I want the lightest possible. Let me take that. You see that? Oh, I think that's going to be just better. Right. I'm going to project that line like so. And I'm going to project that one down. And people, please use a ruler. Okay? They're all vertically downwards and parallel to each other, like you do in engineering drawing. Okay? Alright, so somewhere about somewhere sort of 1/3 down, I'm going to draw a horizontal line there. And that there is my zero line. Okay? Right, so let's see. So that there is my shear force diagram. Now people, now notice there, that's my zero line there. That means I'm going to draw above and below. The shear force diagram is actually a graph with distance on the horizontal axis and load on the vertical axis. I'll say that again. Shear force diagram is actually a graph, and when we draw a graph, we normally draw a graph to good scale. So that is why we're not going to measure the scale, but we're going to draw to a reasonable scale possible. So along the horizontal axis is load, and sorry, my apology, that's nonsense. Along the horizontal axis is distance, and along the vertical axis is load. Okay, that's my zero line. Okay, and when we plot to the top of the zero line, it's considered positive, and when we plot to the bottom of the zero line, it's considered negative. Oh, that's a nasty negative plus. Plus. Ryan, are you tuning in? Okay, this is where we get the theory of where we get the top stuff going. Right, that's my zero line. Right, what's happening at A? We've got an upward load on that point A of 135 kilonewtons. So to some good scale, okay, to a good scale, I'm going to draw my vertical line in. It's 135. So from the zero line going up, 135 kilonewtons. And I'm drawing my line to good scale. Maybe I should just change that slightly. Maybe I should. Let me start again. So that's 135. Notice as I go, I write it in 135. Right, and then from A, let me call that C. From A to C, we have a downward load of minus 15 times 2. Why is it minus? Because from a sign convention, all loads going down is minus. So it's minus 15 times 2. Okay, so from this point start, I pick up my calculator and I punch in 135 and I say minus 15 times 2, and it's equal to plus 105. Okay, it's plus 105. And what does the plus 105 mean? It means the plus 105 is still that amount above the zero line. Okay, so I'm doing that over like so. Plus 105. Right, what's happening at C? I've got a downward load of minus 100. So I've got 105 minus 100 is plus 5. So that means we go down to there, and then it stops just above the zero line. And there's my 5. Okay. And then from C to B, I've got a load of minus 15 times 6. So I'm going to say, so I'm going to say 5. I'm on my calculator. 5 minus 15 times 6 is equal to minus 85. Okay, minus 85. Don't just do what I'm doing, work it out. Okay, minus 85. So I can do something like so. Minus 85. And what's happening at B? I've got a load of plus 85. So what's minus 85 plus 85? It's equal to 0. The shear force diagram must close at the end. Did you hear that? The shear force diagram must close at the end because this whole system here is in equilibrium. And if you get it wrong, and if you just close it, I will check it out. Okay, a lot of students say, oh, just close it there. You won't see. If you get 95 or any other value and you draw to 0 there, I know you fiddled it. Okay, so you quickly go through there. From 0, I got plus 135 at A. Okay, from A to C, I got a load of minus 15 times 2. So it's 135 minus 30. I get 105. And plus means from there to there is still 105. Then at C, I've got a load of minus 100. So 105 minus 100 is still plus 5. So that's just a little bit above the 0 line. And then plus 5 minus 15 times 6 is minus 85. Which takes me to there. Minus 85 plus 85 at B takes you to 0. Okay. So that all of that over there is what we call a positive area. And this area there is we call a negative area. And people there, that is the shear force diagram. Right, so that's part B done. Part C says, draw the bending moment diagram. And by the way, the principal values that it's asking for, it's 135, 155, those are all the principal values. What it just means, it says, show all the values as you go. Okay. Right, next one, this is, draw the bending moment diagram. So let's do that. Okay, and as I said there, so somewhere just below there, I'm going to draw in my 0 line for the bending moment diagram. It's over there somewhere like so. And that's a bending moment diagram. Right, and when we draw bending moment diagram, people, we reverse the sign. So this is the 0 line. So at the top is considered negative and at the bottom is positive. Okay. Top is negative, bottom is positive. Alright, people. So the bending moment diagram always starts at 0 and ends at 0. Okay. Alright, so in order to work at the bending moment at C there, we work at the area of that part of the shear force diagram. Did you get that? To draw the bending moment or to calculate the bending moment at point C here, we calculate the area of the bending moment diagram from there up to point C. So what shape do we have there? We have a trapezium, yes. Okay. And if you don't know what the formula for the area of a trapezium is, you need to divide that shape into a triangle and rectangle and add it together. Okay. And I'm going to use the area of a trapezium because it's easier, there's room for less area. Alright, so that area there, what's the formula for the area of a trapezium? If you remember, the area for a trapezium is half the sum of the parallel sides times the perpendicular distance between the parallel sides. Now you should know that from school already. I'll say it once more. The area for a trapezium is half the sum of the parallel sides times the perpendicular distance between the parallel sides. And what's the length of the parallel sides? A is 135, B is 105, and H is the distance between the parallel sides, which is 2 meters. Okay, so to find the value of the bending moment of that at that point there, I'll say 135 plus 105, half of that times 2 gives me the area, but also gives me the value of the bending moment there. Right? So work that out there and see what you get, and get this and check your value against my value. And what did you get? I got 240. That's right, 240.00. Okay, right, right, people. So, and what value did I get? I got plus 240. Why? Because my area is positive. Okay, and when we plot the bending moment diagram, we plot positive below and negative above the 0 line. Right. Now, people, notice from there to there, I have a UDL. So from there to there, and then to some reasonable scale, I draw, and it's a parabolic curve. Notice from that is a parabolic curve, and it's not doing this, it's curving downwards. Okay, so it's a downward shape, it's a downward parabolic curve, and that value there is 240. I'm going to leave it at 0.00 for sake of space. Right, people? Now, notice if I zoom in here, if I zoom in there, notice there, that piece of triangle there is still positive, okay? So to find the bending moment, now, okay, before I say that there, before we do that, people are very careful. Bending moment starts there, and it's going on toward there, and wherever, did you hear that? Wherever the shear force diagram crosses the zero line, we project a line downwards, because that's where the bending moment diagram graph is going to turn. It's going to turn up or turn down. So from there, I draw a line like so, down like so. And then notice there, it's a straight vertical line parallel to all the other lines. Okay. Now remember I said there, that little piece of triangle is still a positive area. So to find the bending moment at this point here, I need to add the area of that little piece of triangle there to that to find the bending moment value over there. Okay. Right now, what's the formula for the area of a triangle? It's half base times height. Do I know this distance here? No, I don't. We're going to have to work it out. Okay. Alright, so what I'm going to do, I'm going to now see that small triangle and see this one over here. Okay. I have a small triangle. The height of that triangle is 5. And that's base here which I want to find. I'm going to call x. I'm going to call that distance x. Okay. So there's my small triangle. The height of the triangle is 5. The base is x. That height there, what's the height? And notice there, I have a big triangle over there. This line isn't so nice. Let me just redraw it. It isn't so nice. Let me just redraw it quickly there. Here we go. Okay. Right, so that's 5, that's x, and my big triangle here, what's the height from there to there? It's 85 plus 5, it's 90, and what's the distance from there to there? It's 6 meters. Okay, so what I'm going to do, I'm going to find x here using the principle of similar triangles. So I'm going to say the small height over the small base is equal to the big height, which is 85 plus 5, which is 90, over the big base, which is 6 meters. And yippee, from there, I can work out what x is. I'm going to explain that again. A lot of students do all this wonderful work here, and when they get here, they get this wrong, and everything from this point onwards is wrong, and they struggle. Okay, so we want to find x here using similar triangles. So there's my small triangle and there's my big triangle. Okay, so I'm going to say the small height over the small base, 5 over x, is equal to the big height, which is 85 plus 5, which is 90, over the big base, which is 6. Okay, so if I work x out, what do I get for x? X is equal to 0.33 meters. Don't believe me? Work it out and check it out for yourself. So that there is 0.33 meters. So that's 0.33. What is that distance there equal to? It is equal to 5.67 meters. Okay. So now I can work out the area of this triangle. Okay. Because that piece of area there is still positive. Right. Are you tuning in? Are you tuning in? Right. To find the bending moment at the next point here, to this positive value, we add the area of that triangle there. So I'm going to say 240. I'm telling you what I'm doing. Plus, I'm opening my bracket. I'm saying 0.5 times 5 times 0.33. And I get 240.83. I get 240.83. Okay, that's 240. And because there's a UDL from there to there, the graph is actually still going down, down, down to there. And that there is 240.83. Okay. So the bending moment at C is 240.0, and the bending moment at the next point is 240.83. Can you see the bending moment is still getting bigger? So therefore the curve is still going down, 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 and it is at this point here where the graph will turn and go back up to 0. Right. Now from here, the bending moment diagram should go back to 0, but we're not going to assume that. We're going to check it. So what we're going to do, how do we find the bending moment at this point here? We say plus 240.83 minus. Why minus? Because this graph is minus. So I'm going to say 240.83. It's on my calculator. I'm going to say minus half 5.67 times 0.85 and see what you get. Sorry. 240.83 minus half times 5.67 times 85. So I'm going to say minus 0.5 times 5.67. I'm telling you what I'm doing. Times 85, and I get minus 0.15. I get minus 0.1, a very tiny value, and for us that's good as 0. The 0.15 is there because of all the rounding off along the way, and because there's a UDL going from there all the way to the end there, it's still a curve, and the curve is doing this, and it go back. Oh, that's a bad. Let me just change it. I'll draw the curve in again. So the curve is still downward curving, and it's going to 0 there. Okay. And all of this here and all of that under there is a positive area. Okay. So let me repeat it again. We start at 0. How do I find the bending moment here? I find the area of that shape over there. And what's the formula for the area of a trapezium? It's half the sum of the parallel sides times the distance between the parallel sides. So 135 plus 105 times half times 2 gives me plus 240. And why is it plus? Because the shear force diagram is parallel over there. And then to that area there, to that value of the bending moment diagram there, I add the positive area of the triangle there. So, and we found from similar triangles that the distance of the base of the triangle is 0.33 meters. So 240 plus the area of that small piece of triangle gives us plus 240.83 kilonewton meters. Okay. And that's a downward curve all along the way because there's a UDL all along on the beam there. And then from there to there, we add the negative area of the triangle. So it's 240.83 minus half times 5.67 times 85. It gives us minus 0.15, and that for us is good enough as a 0. And we draw the curve from there, and it ends a 0 there. Okay. So people there, we calculate support reactions, we drew the shear force diagram, and we just drew in the bending moment diagram. Okay. And by the way there, if you look at the values there, just some notes. That there is called, I'll call it bending moment max, because that there will be the maximum bending moment for this beam. Okay. And why do we want to know that? Because all of this here is just analysis. Okay. And now from this point onwards, we design the beam. Meaning that we're going to work at how much steel must go in the beam. Okay. And this magic number here is the number which beam designers use to work at your area of steel which can carry the load in the beam. Okay. So people there's our beam. We calculate support reaction. We do the shear force diagram, and we do the bending moment diagram there. And that there is the maximum bending moment there. Okay. Okay people, that's the end of this lesson. And I'll see you in the next lesson.